Everyone. All right, everybody, welcome to Lecture 6, Clustering Analysis and K-Means. These lecture slides were prepared by Mahdi Ruz-Bahani from Georgia Tech. I'm Stuart Isaacs. I'm going to be your lecturer today. Let me go ahead and minimize this a bit so that we can see these slides. So today we'll go over just the idea of clustering in general. We'll talk about distance functions. That's just a way for us to look at dissimilarity. Then we'll go over the K-means algorithm, and we'll analyze what the K-means algorithm means. So essentially, clustering is just dividing an object into groups that are similar or more similar to those in the group than they are to those outside the group. So if you look at these images on the right, you can see that these are in 1, 2, 3, 4, 5 different clusters. And even though we can't see the images very well, we can see that like these are pretty blue, whereas these are more like orangish and these are green. So based on this image database, we've clustered these images into 4 different clusters based on some metric of similarity. And so we can look at another example of clustering where we have flags. You know, here we have blue flags with this insignia right here from the UK, since they're colonizers, as well as the other groups of clustering, like Niger and India. They have a similar color pattern and stripe pattern, whereas France and Serbia look pretty similar. And then we can see that for linguistically as well. So it's not just something that's visual. We can cluster based on a lot of different dimensions of evaluating something. So here we look at language. We're looking at the name Peter in different languages. And based on the color, you can see that they've been clustered based on some metric of similarity. These are all languages, I guess, close to the European continent. And you can see the similarity in clusters here. Another way we could look at cluster is with animals. So one way you could do this is you might draw a cluster here versus here, right? On the left, we have primates. I'm not sure the word for that. Whereas on the other side, we have a cow. But you could also cluster it a different way. Perhaps you could say, okay, well, who's walking on 2 feet versus 4? And that might look something like, I don't know, this. I don't actually know these animals very well, but it doesn't really matter. The clustering is arbitrary. It's based on whatever your metric is of similarity. Are there any questions here?
No.
Okay. Here's another example where you could cluster hand digits. I don't really understand this slide very well, so with your permission, I'm just going to keep going. Okay. So this is just another example of the subjectivity of clustering. There's no objective similarity measurement. It's whatever you decide you care about in terms of similarity. So here we have these Simpsons characters, right? And your similarity measure might be, you know, family versus employees, or you might look at something like people's sex. So you might have females versus males. Right? And so here's just another example of really interrogating the subjectivity of similarity. I mean, they look pretty similar to me, but I mean, if you're looking at, are these the same animal or not, these are pretty different, but the overall like color scheme and hair pattern looks pretty same to me. So it's a fun example. So in general, you're gonna pick your similarity or dissimilarity function, and they're going to have some algorithm that's going to group objects based on that function. And so points within a particular cluster are similar, points across clusters are not similar, as we've seen. But then it leads to some questions which are, okay, how do we represent objects? What is the function that we're going to use for the data? And then when we're implementing this algorithm, what are the steps? So that's the overview on clustering. Before I move on, are there any questions? Okay. So let's talk about generally what a similarity function must be. And so here we have some properties that we would like in a dissimilarity function. One of them is symmetry. Basically, this to that is the same as that to this. So you can't claim that Alex looks like Bob, but Bob looks nothing like Alex. If you reverse it, they should have the same outcome, right? The similarity between X and Y should be same, or the dissimilarity in this case, should be the same as dissimilarity of Y on X. That just makes sense, right? You don't want your data set to flip or be different based on which parameter you're evaluating first. There's also this idea of positive separability. That means that the similarity of something should only be, or the dissimilarity of something, d of xy, should only be 0 if x and y are the same. If you can't tell, otherwise there are objects that are different, but you cannot tell apart. I think that makes sense. And then finally, we have this triangle inequality. Basically, if I were to take this to be A, and this to be B, and this is C, we want it such that this is A, B, C. C must be less than or equal to the sum of A and B. That's the triangle inequality. We would like that to be true. Otherwise, you could make these comparisons such that Alex is like Bob, Alex is very like Carl, but Bob is very unlike Carl. And that just wouldn't jive with the data sets that we're working with. We don't want that. Any questions here? Okay. Keeping it pushing. Oh. All right. So one way that we look at similarity or dissimilarity is by using distance functions for vectors. So you might have data points where you have real numbers of up to, I guess, length d. And so you might have your x data point, x1, x2 onto d, your y data point, y1, y2 onto yd. And you might look at the distance between these data points. So you might compare x and y. And you could do what's most commonly used is what is commonly used is Euclidean distance. So that's kind of the same way you do geometric distance. You're taking the difference of the 2 points, you're squaring it, and you're taking the square root of that. And so this is for all the points within your vectors. This can be generalized into the Minkowski distance. So rather than squaring the difference and then taking the square root of that sum of all the differences within your data points, you just generalize it to some p. So you take it to the power of p, and you take the p root of that, right? And so with that understanding, the Euclidean distance is just the Minkowski distance with a p value equal to 2. Two other distance functions that are going to come up in this lecture are the Manhattan distance, where p equals 1. So instead of taking the root, you're just summing up the absolute value of the differences. And then we have this inf distance where p equals infinity, and this is the maximum distance in your data set. Any questions here?
No.
Okay. So here's an example. We have these data x and y represented on this 2D graph. And we can do the Euclidean distance. This is what you're most familiar with. You take 4 squared plus 3 squared, you take the root of that, you get 5. Okay. Manhattan distance just takes the sum of these, without squaring it or taking the square root. So you do 4 plus 3, you get 7. And then inf is just taking the max value of all these different distances between x and y. So because this is 2D, we only have 2 points, 3 and 4. 4 is the biggest therefore we go with 4, right? That maps onto this pretty well. Okay, that's just an example of using 3 different distance functions. And again, the context is we're looking at ways of evaluating dissimilarity between data points. So there are some problems when it comes to Euclidean distance. I'm still trying to wrap my head around this, but basically, because we're human, we have some biases in how we think that data is represented within a certain, I guess, multi-dimensional space. And so this might require more reading for the curse of dimensionality. And I wish I could break this down for you a little better. Sadly, I can't. But essentially, you might have data points that are randomly distributed within this space. So right here, we have a 2D circle. And let's say we have some Z and Y on the outskirts. And I probably should have taken a little more notes here, but one thing we can think about is this outer shell. And go back for a second. Okay. Okay, so what we'll find is that if we look at the volume that this outer shell takes up, and let's just go ahead and map it onto this 3D representation. So we know that the volume is going to be equal to 4/3 pi r cubed. And we can go ahead and simplify that to C r cubed. Are we with me?
Mm-hmm.
All right. Then we can say that the volume of a shell, so this outer shell in 3-dimensional space, is going to be equal to the total volume, so some constant C, minus, and assuming that R is the distance from the center to the innermost part of the shell, C r cubed. And then if we were to take the ratio between the, I think it's the V over V shell, it's going to be equal to, I think it's 1 minus, am I doing this right? C r cubed?
It's V shell over V.
Okay, that's right.
Because you want the percentage that's in the shell compared to the total volume.
V shell over V. Okay, and then can you just read out what that equation is supposed to be?
Yeah, I think it's 1 minus this is going to cancel out.
It's on the lecture. Let me look it up.
Oh, I think. Oh, yeah. Okay. I think the volume.
Shouldn't it just be?
Is it r cubed?
C over.
Yeah, it's just gonna be.
Okay, let me just verify this. Y'all can look it up if you want. One sec. Can y'all still see my screen?
Mm-hmm.
Can you see what I'm doing?
No.
Okay, here it is. CRD. Okay, so we're going to generalize it to 1 minus C. There we go. This should be it. CRD. Okay. and where D represents the dimensionality of your data set, right? So we have three-dimensional space here. So we end up with D being 3. And when you go ahead and calculate this, you end up with a pretty low percentage, like, I don't know, 15. I don't actually remember the exact value. Look it up. It's hard to read in the lecture. 0. I don't think they actually wrote it. But basically the idea of the curse of dimensionality is that as you increase the dimensions of your data set, then the volume that the outermost shell takes up relative to the volume of the entire dimensional space becomes larger and larger. So as you increase from 3 dimensions, you might end up where the majority of space or volume in some dimensional data set is located in the outermost points. And when that's the case, your Euclidean distance, the geometric distance between points, or between the center and the point in this example, isn't going to be that helpful because most points fall into the outer shell. So you get these very close distances. You would say dx and y and dx and z look pretty similar, but because you have 7 dimensions, your Euclidean distance isn't a good measure for the dissimilarity between those. So does that make sense? Like the more dimensions you get, because we're human, it's hard for us to represent the data in a way that we understand intuitively, because we only understand 3 dimensions in geographical space. So higher order dimensions means that the V shell is going to take up more as a percentage of the total volume. So why don't I go ahead and click on this so we can look at this. Assuming I still have free.
You're
stuff.
only showing like one page, which is I think your.
Yeah, and that's fine.
Okay.
Let me go ahead and share another screen. So.
Is it the article, the Medium article?
Mm-hmm. So I'm going to stop share, and I'm going to share this Medium article, which for some reason they don't want us to have a bunch of these for free. So D represents the dimensions, and as you can see, when we have low number of dimensions, the outer shell doesn't take up that much, but it pretty quickly goes up where, around 200 or I guess 400, the outer shell represents most of
the
volume of this higher order dimension data set space.
So you were saying that means that then now the distance is also greater, or is it distance from the center, for example, is also greater as the dimensions are increasing?
Well, I'm saying it just becomes a bad measure of dissimilarity because you're looking at the distance from the center of, let's say, 2 different points that are like on the outermost edge of whatever your dimensional space is. You might get a similar value. You might try and cluster them together, but the reality is most of your data points are in the outer shell because look at the volume. So now your Euclidean space clustering is failing you because it's not giving you an accurate, or it's not giving you a good metric of dissimilarity anymore. Any questions about this?
No, makes sense.
Okay, then I'm going to go back to the lecture notes.
So is it just that it's a natural, like it's just like a natural, I don't know, phenomenon, or just like a natural thing that's happening where if you have data that's of higher if you have a data set of higher dimensions, it just naturally is biased towards being in the outer shell?
I guess I'm not sure if I would use that word, but you have to keep in mind that the outer shell represents a larger and larger fraction of the total volume. So if you had, just evenly distributed data points throughout your entire space, most of those points will be in the outer shell because the volume of the outer shell is a huge fraction of your space.
Okay, got it.
Okay. Let's talk about Hamming distance. This is fascinating. So we talked about Manhattan distance before, where that was just the largest difference between two data points. And so in this example, we're going to represent X and Y. These are binary numbers, or excuse me, these are binary vectors. And there's like 17 digits. So X, the binary vector for X is 0, 1, 1, 0, 0, 1, you know, and so on. And the Manhattan distance is just going to compare each of these. And we're going to say, okay, well, this has a difference, 1. This is a different 2, and so on until we get to the end. And the distance is just the sum up of all those different parts. Does that make sense?
Yeah.
That
makes sense.
Okay, so it summed up the max difference between both of those vectors. Another thing we can think about is another dissimilarity function you might use is edit distance. So let's say you're no longer working with, or you might be working with strings, for example. And so your X vector is the word intention, and your Y vector is the word execution. And you've defined this function, edit distance, as the following. You transform one into the other, and depending on how much effort it took to transform it, that's the dissimilarity of the two. So here they have different weights. They say if you delete one, it costs you 5. If you substitute a letter, it costs you 1. And if you insert a letter, it costs 2. So let's look at this. We have this I. This is going to need to be deleted. All right. These are going to be the same. Or no, you're substituting N with E. You're substituting T with X. Right. This is the same. You have to insert a letter here. You're substituting this, but these parts remain the same. So we'll sum up those. We say we have 1 deletion, 5 times 1, because the cost is 5. And then we're adding that to the total number of substitutions, 3, plus the cost, 1. And then we had 1 insertion here, and the cost was 2. So now the dissimilarity based on this edit distance function we defined is going to be 10. Why don't we go ahead and do another example? So I have the word, oh, yeah, okay. I have the word intention again. Okay, let me actually try this again so that I can account for how hard it is to write. So I have the word intent. And I'm going to change it to insertion. And we're going to assume it's not case sensitive because I didn't write case sensitively. And so if we look at this, we see that this is the same, this is the same. Okay, this is different. We had a substitution here. So let me just demark an S. We had these are the same. We have another substitution here, S. These are the same, these are the same, these are the same. So when I look at my dissimilarity function, D of X and Y, I'm going to say that, well, we have 2 substitutions. So I have 2, and the weight is 1 times 1, which gives me a total dissimilarity cost or value of 2. Did we follow there? All right. So those are some examples of looking at dissimilarity or distance functions. So now we're going to talk about the k-means clustering. We have an example of k-means here. Basically, we're representing an image based on its intensity or color alone. And depending on how we do the k-means, you might end up with an image like this, an image like this. I think it's better to look at this example. So we might say we're going to use the k-means clustering algorithm with 11 different segments or clusters. And based on that, it's going to group this into 11 different color values. and cluster them. So now when we look at this image, instead of having independent RGB values, every single pixel is going to fall into one of these 11 clusters, and it's re-represented in this way. We'll talk about why we might do that a little bit later. We have another example here where we have the original image of a castle on the left, and now we've done some clustering where we've reduced the number of color possibilities to, I don't know, what, 5 or 6 in this, and every single pixel is now represented by whatever the centroid color is for that cluster. And then we have similar images where I'm not actually sure what's going on here, but I'm going to assume that these have been clustered as well. So why don't we take a look at what k-means is. I'm going to share my screen now. This is a nice visual. So on this metric, we can choose to have cluster points or randomness. So why don't we go ahead and do this? What's new points again? Okay. So let's take the worst. Well, let's actually start in the middle. I think this is going to make the most sense. So the points aren't very clustered here. And what we want to do is use the k-means algorithm. And what it does is there's 2 different steps. It finds the centroids, finds the closest centroids for all the data points, and then updates the centroid to be, I guess, reduce. We'll talk exactly what it is, but it's going to find the closest centroid for all the data points, and it's going to update the centroid. So we're going to do the first step, find the closest centroid. So now you can see that all the points are colored to some centroid that has been arbitrarily chosen, and then we're going to update the centroid. Right, now they move. And then we're going to do the same process again. So we're going to recolor based on what the closest centroid is. And then based on some maximization function, which we'll talk about later, the centroid moves again. And we keep doing this until they stop moving. The word we use for that is convergence. So several steps. Will this converge? It should. They have now converged. K-means clustering. And you can see some intricacies with this. This is kind of fun. So I could have more randomness, and maybe I'll define, let's say 4 clusters, but I'm only going to let, I'm only going to have 3 centroids. I can do this process again, and it's just going to do its best. I think the fascinating thing is if you have actual clustered points, and let's say we have new centroids, right? You don't always end up using all the centroids for the data. So let me do new centroids again. We had 2 last time. Okay, this time we had 3. Let me do new centroids again, 2 again. Are you seeing what's happening here? Like when your data set is super clustered, your k-means might converge on a solution where even if you have the right number of centroids versus the clustered data sets, your clustered data, you still might converge on a solution that doesn't have every centroid on each cluster. Are you seeing what I'm saying?
So are you saying that if you had like four what is it?
Centroids?
4 centroids as well, like you might get some results like this too? Or will it?
Let's find out. So we have 4 centroids, 4 clusters, but we've only assigned the centroids to 3 centroids to a cluster. 1's been left out. Let's try it again. So every time I click new centroids, the centroids are placed in some arbitrary place within the space. Then we run the algorithm. All right, in this case, we've only had 2 of our 4 centroids put on our data sets, put on our clustered data, even though we have 4 centroids and there's 4 clusters, right? Whereas if right, and so I could do new centroids again, I get a different result, right? New centroids again, now I have 3. Whereas if, let's say there's a little more randomness in it, Okay. One, I'm using all 4 of my centroids. And I'm willing to bet that with new centroids, my answer is going to look pretty similar between all of them. Well, maybe that's not true. But your answers aren't always going to come out the same, which is fascinating to me.
Yeah.
Okay.
It makes sense because the centroids are sort of randomly generated.
Yeah. So with this particular algorithm, that is one of the, I guess that's one thing you need to consider. So now that we've looked at the example, let's talk about what was happening. Bayon, did you have any questions before I move on?
No, I'm good.
Okay. Okay, so what is this k-means algorithm that we've seen? What we're going to do is we're going to initialize however many clusters we're specifying randomly, right? So you saw the centroids. Well, okay, we're just going to assume that there's k number of clusters. And there's 2 steps to the algorithm. First, we're going to decide the cluster memberships of each of the points x by assigning it to its nearest cluster center using some distance function here. And whatever the minimum of whichever cluster minimizes our dissimilarity function here. In this scenario, we're using Euclidean distance. Do you see that? Where we're taking the, is this Euclidean distance?
Yeah, it is. It's the 2 norm, so it's, well, yeah, it's not specified which norm it is, but it's assumed that it's a 2 norm, so it would be Euclidean.
Okay, so in this scenario, we're using Euclidean distance, I think, or 2 norm, and whatever centroid minimizes it, we're going to assign it to that cluster. And then what we're going to do is we're going to adjust the cluster center such that, I'm trying to remember the best way to put this. We're adjusting the cluster center so that it's at the centroid of all the points that have been assigned to that centroid.
Yeah, so you have, like, after step 1, you have a certain number of points. Let's say let me not say n. Let's say m points that are assigned to cluster J, and then you take those m points and you basically find the mean of those. The mean of those points. So you can see this
Right.
1 over, like, basically the number of points that are assigned to that cluster, and then the sum of the points themselves. And so then you get the mean point, basically, and then now that's your new center.
Exactly. And you're getting the mean point for k different clusters.
Yeah.
K-means algorithm. And so now you're going to continue this. So now you're going to continue this.
Poetry.
You said what?
It was poetry.
Exactly. Well done for the inventors. So you're going to repeat this 2-step process until your cluster centers stop changing. So that's what we're going to define as our convergence here. I think what's important to note here is that these are a little more generalizable than, one way to look at this is to describe this as finding the expectation and then this part, step 2, is the maximization. So I'm just going to write max because it's really hard to write on this. Yeah, so in the reading, I think it breaks it down a little more mathematically. But essentially what's happening here is that you can generalize this to say that we're finding the expectation of some distortion measure. And then we are maximizing we're doing some type of maximization in the next step to move our centroid. I think it's important to know, so we can generalize this as a EM expectation maximization algorithm, and where k-means is just one particular form of this kind of algorithm. And that's important to know because next week's lecture, we're going to dive deeper into other EM algorithms that I guess have different properties, but k-means is commonly used. So again, this is step one. We have some data set represented by the blues, and then we have some arbitrary centroids that we've placed onto the data set. The first part is the expectation part, where we assign the data points to the nearest centroid. So all the greens are assigned to C1, all the reds are assigned to C2, and so on. And then we're going to find the mean, right? The mean value for all these data points. And we're going to adjust our centroid to be at that mean value. So now we see that C1 has moved to be at the mean of all the green points. Then we want to repeat.
Did
So
we see how we are selecting C1, C2, C3?
yeah, C1, C2, and C3 are arbitrarily placed onto, well, for now, they're arbitrarily placed onto your data.
Oh, okay. And then they're updated?
Then they're updated,
Okay.
right? So it's a very, well, I don't know what word to use to describe it. There are smarter ways to place your centroids, but we're not going to talk about those yet.
I got it.
So we have it here where we've moved the centroids. This is the first iteration, right? We assigned, we moved them, then we go through it again. So you're reassigning the colors. So if you look here, this was previously green, now it's red, right? And you can see something here, this is previously green, blue now. So we reassign the colors for step 4, right? That's that assigning the data to its nearest K or nearest centroid, and then we adjust the centroid. So it was here, now we're shifting it to the right, bang. And so on until it converges. Does that make sense? Okay. So now let's talk about some of the, let's talk about k-means a little more. So let's answer question 1. Well, why don't we do this? Bam, why don't you sign up for one question, and then Nosa, you sign up for a different question. Bam, which one do you want?
I'll take the first one.
Okay, and then Nosa, you'll take the second. So let's take 1 minute to look over these questions, think about it. If you have questions about the questions before you answer the question, feel free to ask them, and then we'll go over the answers. So I'm gonna put 1 minute on the clock, or 30 seconds really. Okay, do we have our answers? All right, bam, what do you, will different initialization lead to different results?
My intuition says no. Only because regardless of where you end up putting it, you'll always converge to the natural clustering.
Okay, why don't we test that? So let's go back to our example. I'm going to do new points. Let's make it obvious here. We have 4 new points. Okay, 4 clusters. I think we can see them all, right? One's hiding here. 4 centroids. We should line them up, right? So I'm going to go through the algorithm. Okay, we've ended up with this. We have 4 centroids, right? Red, green, orange, and blue up in this corner. 4 clusters, but we've only assigned the clusters to 3 of the centroids. So I'm going to do new centroids. right? Okay, so now we've assigned 2. So I think this kind of disproves the no, right? Depending on where you put your centroids, you're going to get a different result.
I see. Okay.
So let me go back to this. So the answer here is sometimes, right? Depending on your data set, how clustered your stuff is, you might end up with different results, depending on where you initialize your centroids. So,
so then, so why would you, like, I guess, if you're like, why would you ever use this algorithm if you don't have any consistency in how you're like, I guess if it's so dependent on your initialization, then like you don't have any consistency in predictions, right? Or like how you're clustering things.
Yeah, that's true. I think it depends on how you need to characterize your data set first to understand if this is something that you can get away with using k-means on, right? We saw that for very clustered data sets, maybe k-means might not be the best approach to clustering because you might end up with wildly different results. But sometimes people will start with k-means to cluster, and then they'll use another clustering algorithm on top of that. And I think that might end up with, I'm not exactly sure how that works yet, but my understanding is if you did that method, you'll end up with a final result that might be more consistent than otherwise if you just did k-means.
Got it. Okay.
You can also initialize differently. Here they're just randomly initializing to any point in the space. You can actually pick a data, like a random data point to start as your clusters, and you might get better results, or just pick random points that are closer to the actual points. Because usually when you have like a floating centroid that doesn't have any assigned points, it's because it was initialized very far from the points.
Okay.
It sounds like with some smart initialization, the k-means algorithm can be a little better. Nosa, will the algorithm always stop after some iteration?
Yeah, I'm inclined to say yes, or like sometimes I can't really think of a situation where it wouldn't stop, but I'm sure there is one. So I'll go with sometimes.
Okay. So the answer is yes.
Oh, yeah.
Because and one way you can think about that is that there's going to be some choice for each data point. It's going to be assigned to whatever centroid. And even when there's, data that are in between, very obvious clusters, those will get sent to one or the other. And at some point, even when you're doing the algorithm, it's going to stop moving. I guess I don't really understand why that's the case, but the answer is yes.
So the I guess one way to think about it is that the backbone of k-means is still an optimization algorithm, and in every step you take, whether it's the expectation or maximization step, you are minimizing your optimization, your loss function or your objective function.
Mm-hmm.
Oh yeah.
So in the first step, what we're doing is assigning the data points to the clusters. So you can think of it as you're minimizing your objective function. You're assigning the data point to the closest cluster. So regardless of what cluster it was assigned to before, the new cluster you're assigning to must be equal or less distance than the old cluster. In the maximization step, you are moving the clusters to the means of the data points. And by nature of a mean, you are also minimizing the distances than what they were before. So that's why it always has to stop, because at some point, because it's a minimization, you're
You're gonna reach the minimum.
You're gonna reach convergence. But it's not a global solution like from the first question. I think that's the point here is it's gonna stop eventually, but it's not necessarily gonna be the global solution. It could be a local solution.
That makes sense.
I think the text has this chart where J is your function of the objective function, and each step you take, you're decreasing the value of the objective function until you reach some minimum. I think I drew it like an asymptote. That was wrong with me. At some point, it reaches some minimum value, and you're just there. So this should be a straight line. Any questions before we move on? Thank you for clearing that up, Kevin. That was great.
Nope.
Okay. So yeah, the formal way of stating this clustering problem, given endpoints, we're going to find K clusters. We're going to assign each data point I to one of these clusters, and such that the average square distances for each of the data point to its respective cluster center is small. We're minimizing the average square distance between each data point to the cluster center by choosing a cluster center that minimizes this function.
Yeah. Also, I want to note, just for future reference, I think I was wrong about this. When the norm is written like this, it's not necessarily the 2 norm, it's just a generalized norm, so you can place any distance in that. So don't hold me to that 2 norm thing. Generalized.
Okay, thank you. Okay. Clustering is NP hard. I've tried to wrap my head around what NP means. I don't have an advanced understanding enough to describe this. But you can I don't even know how to walk through this, but essentially there's a lot of clustering possibilities. And like Kevin said, you're not always guaranteed to find the global minimum. You might find yourself in the local minimum. And an example of looking at, even for 3 data points, you're going to have in 2 clusters, you're going to have K to the N possibilities of cluster combos. So that will be 2 to the 3rd, which is 8. And what I can do is go ahead and write that out to make it explicit. So if you given points A, B, C, and 2 clusters, what we could do is we could assign A, B, and C into different clusters such that A is cluster 1, B and C are cluster 2, and so on. So I could have B and C as their own clusters. This would be A and C. This would be B and A. And then you could also have it such that basically the reverse case. So B, C versus A, AC, yikes, versus B. Let me scroll down a bit. What's left? BA versus C. And then similarly, we could start lumping all or nothing. So you could have nothing here, ABC, or you could have ABC here and nothing here. So that's 1, 2, 3, 4, 5, 6, 7, 8 clustering possibilities given 3 data points in 2 clusters. So lots of options. And I think what's happening in the previous slide is they're trying to comment on that by, oops, let me delete these annotations. Can I clear my drawings?
Yeah.
Okay. So what they're trying to comment on is that because of all these discrete assignments, there's a lot of possibilities, and that's NP hard. I'm not sure what NP hard means. So Kevin, if you want to clear up that, that'd be very valuable.
It's not crucial for your understanding of machine learning, so I wouldn't stress it.
Okay, so fuck it. All right, convergence of k-means. Will it oscillate? No, right? We're minimizing it. Our objective function is going to reach some value, and then that's a minimum. So we wouldn't expect it to oscillate. Each iteration of k-means decreases the objective. That's what Kevin said earlier. Right, in both of these steps of the algorithm. We could use big O notation to understand the time complexity of it. As a practitioner, more so than someone who looks at this, I don't really know much about this. But Kevin, is this important?
Yeah, I'd say so. 'Cause
Yeah, usually
Is
it's
it
pretty
something?
important.
Yeah, it's something to keep aware of for anyone who's going to, write code or write algorithms.
just from like a practical standpoint, if you work with really large data sets and you have some sort of like computing limit, like resource limit or something, these time complexities are what determine whether your algorithm would suffice in meeting that like maximum or whatever. So it might not actually matter that much if you're working with like really small data sets, but very large data sets, it could be like the limit on how long it'll take you to actually like train your data set or train whatever you're working on.
It sounds like because you're computing the distance between the centroids for every single data point, so right, you end up with, you have to do for k clusters, n different distance computations. So you get a big O of k and n. And then if there's multiple features, then you have d for each feature. So if you have a huge data set, I think you start to run into memory issues here with your RAM, according to the book. And then when you're computing the centroid, each instance vector gets added once to some centroid. OND. Yeah, so I don't really understand these parts, to be honest, but and based on my understanding of Big O, I guess if you have a large data set and a lot of centroids, this can get pretty ugly pretty quick. So even when you have the number of iterations, so as you're minimizing your function, you're going to do like 100 different times, right? That's factoring into your Big O, as well as the number of clusters, the number of data points, the number of dimensions. So keep this in mind.
Yeah, it's very inefficient. Is kind of what they're saying.
Yeah, I think there's smarter ways to get it done. There might be smarter ways to cluster when you have huge data sets with lots of these parameters. And the last slide here is, you might be questioning how many Ks you should choose. And one way to look at that is to compare your final objective function value, what they call distortion in the book, between different numbers of clusters, and you're aiming for the elbow. So this is when you get a pretty low objective function, where like you start to have marginal benefits as you increase the number of clusters, or no benefit at all once you reach a certain number.
Okay.
That's everything. Any final questions?
And the objective function here is the sum of all the distances? Or yeah, the sum of all the distances from their centroids?
Yes.
Okay.
Yeah. Yeah.
or not all the distances from the all the points from the centroid, but I think you understood by that.
Yeah.
Okay. Cool.
Okay. Great. Well, thanks for coming to the lecture. Hope you learned.
Nice. Is there a